As students from Los Angeles, we are intimately acquainted with freeway systems. We are conscious of our current dependence on these systems and their health and environmental impacts. However, we are also optimistic for the possibility of these spaces to be transformed into multi-benefit infrastructures.
The United States has the largest road network in the world. Highways account for nearly 50,000 miles of paved linear space, with huge potential for additional noise barriers. Across the U.S., 8 billion cars use these roads every day, contributing to about a quarter of our greenhouse gas emissions. Highways generate noise levels just below those that cause hearing damage, yet significant enough to have lasting impacts on mental and physical health, including heart disease and childhood asthma. Unfortunately, these impacts disproportionately harm lower socioeconomic populations, who are more likely to be located near high-frequency roads. While these problems are not new, they represent ongoing injustices within the structure of our cities and represent a lack of urgency for integrated abatement. By studying symbiotic species relationships as a means of intervention, our project aims to create an approachable solution to immediately mitigate these injustices and to begin to generate new visual representations for imagining the future of our built environments. The project began by researching the existing symbiotic relationship between the Elysia chlorotica species of sea slug and the Vaucheria litoria species of algae. Analysis to understand the success of the species relationship included the biological systems, the functional processes, and the conceptual relationship. The research into the species environment identified shallow water ecosystems of coastal regions as the basis for study. This included a variety of salinity ranges from salt marshes to inland freshwater sources. The key factors of all these environments is access to sunlight, carbon dioxide, and additional nutrients for algae photosynthesis. Situated in these environments, the slug can access and extract algae DNA to incorporate into its own DNA structure via horizontal DNA transfer. This allows the slug to also extract and store algae chloroplasts within its diverticula, triggering metamorphosis. The sea slug is a chimera, able to integrate species from both Animalia and Plantae kingdoms for mutual benefit. The animal, the sea slug, benefits by taking on the characteristics of the plant, becoming plant-like both in form and in function, allowing the slug to be photosynthetic to produce its own fuel. The plant, algae, benefits by evolving to survive within the Animalia kingdom. The highway, as a design context, demonstrates interesting parallels to the environment of our symbiont species due to the correlation between the systems. These linear open spaces are abundant with sunlight, carbon dioxide emissions, and potential water runoff. Could the highway system become chimeric and act like the slug by promoting the growth of other species within its bounds? Through collaboration over time, could it create a more ideal environment by serving greater functions, including pollution filtration, noise reduction, fuel generation, and ultimately address socioeconomic inequities? In our search to find a parallel symbiont species with non-aquatic applications suitable for the highway context, our project identified lichens. Where the sea slug become both animal and plant, lichen incorporate algae to become both fungi and plant. Lichens are resistant to desiccation, with water presence activating photosynthesis. Lichen varieties range in terms of resilience to pollution, making them indicators for health and success of the overall system. Based on our research, we began earlier variations for algae-based models, including algae tiles, fognet systems, and storage systems. However, each of these systems were too narrowly focused, required intensive engineering, ignored important socioeconomic conditions, and depended on water sources incompatible with the highway system. Our intervention utilizes the same components as the lichen systems. The layers of environmental protection, photosynthetic growth, and structural support are translated into our proposed project, the acoustic tile. These components become the protection structure, living system, and support structure of our living prototype. The integrated approach provides a nourishing habitat for symbiont species within the context of the freeway infrastructure, resulting in the overall well-being of adjacent communities. The base material of the tile is clay, selected for its natural, sustainable, and accessible qualities. Clay's microporous structure retains water and exhibits pollution filtration characteristics. It can be 3D printed or handcrafted, allowing for the code or model to be open sourced. The tile form encompasses various elements, while the overall wall meets U.S. transportation requirements to be non-distracting. Primarily, the form mimics the surface structure treatment of the Namib desert beetle, seen in the tile's grooves and spherical shapes acting as hydrophilic and hydrophobic surfaces that strategically move water. These formal attributes create variation for shade and sun exposure, producing a range of conditions for fungal and plant growth. Smaller scale grooving resulting from tooling marks on 3D printed tiles or natural variation on handmade tiles create micropockets which attract water and variegated surfaces to encourage root adherence. The living components colonize the tile in stages, altering the microclimate of the vertical surface, sequestering pollution, and creating acoustic absorption over time. Algae plays an important role in the initial mitigation of pollutants, including sequestering carbon dioxide. This also involves blue-green algae, a nitrogen-fixing cyanobacteria, which additionally provides algae sources for lichen structures. Crustose lichen, the most pollutant-resistant lichen species, would colonize the tile and alter the microecology. Then, lichen varieties of fruticus and folios could become established, providing additional pollution mitigation and enhancing the tile performance. As biomass accumulates, it would perform as an acoustic barrier for high-frequency sounds. Lower-frequency noise would be absorbed by a small air cavity at the back of the tile, following the Helmholtz resonance principle. The utilization of the low-cost hyper-services sensors embedded within each tile integrates technology into the living system to better monitor the health of both the individual tile as well as the overall system. The data would determine whether the tile remains on the freeway, is to be harvested for its acoustic or biofuel properties, or requires replacement from damage. The project was designed as a low-impact passive system, creating a variety of spaces for water retention and sunlight variation. However, for more difficult living conditions, future modules are being studied, including methods to collect and store water runoff within the cavity of the tile. Acoustic tile asserts the need for biological thinking by welcoming natural systems within our man-made infrastructural networks. It asks whether these systems can coexist and collaborate towards healthier and more equitable futures. On a practical level, the project aims to be a low-cost and easy-to-implement system to provide relief for environmental and noise pollution. Yet it also confronts the socioeconomic inequities constructed within our urban fabric. We are not naive to suggest this project is a solution to these injustices. Rather, it begins the active process of healing by providing a method for interventions to occur at a government or grassroots level. The expanses of living walls alongside the very veins associated with progress bring awareness to a different potential where biological and technological systems are not set in opposition, but can coexist for mutual benefit. Even in a future scenario of improved technologies and reduced dependence on cars, the system creates a lasting mutuality between our infrastructure, our biophysical world, and our most vulnerable communities.